So next speaker is Thomas Koberda, and he will talk about differential topology and first order rigidity.
Thank you all for coming, and it's a great honor to be here, so thank you to the organizers for inviting me. So I'm going to talk about some work that was recently completed jointly with Nuez González and Sang-hyun Kim, who are both at Kios in Seoul. So let's let M be a closed smooth manifold. Which I will, just for convenience, although it's not strictly necessary most of the time, I'll assume that it's also connected. So now, if you have any R, a parameter between 1 and including infinity, then you can consider this group of CR diffeomorphisms. And inside here, one has this canonical subgroup. With the compact open topology, you have a connected component of the identity inside here. Okay, and when I say CR diffeomorphisms, let me just clarify a little bit what I mean for non-integer values of R. So if we write R as k plus tau, where here k is a natural number and tau lies between 0 and 1, then what we mean here is when we say a CR diffeomorphism, we mean is by definition a CK diffeomorphism with the kth derivatives being tau Holder continuous. So that's some sort of interpolation between CK and CK plus 1 diffeomorphisms. So there's this interpolation isn't really perfect because if one takes tau to be equal to 1, then the Holder inequality just becomes the Lipschitz inequality, which is not the same as differentiability, but it's so CK plus 1 is not then the same really as CK plus 1, but it's just a technical issue that I'm sort of going to sweep under the rug for most of this talk. Okay, so we have these groups which are of interest intrinsically in differential topology. And so if you fix M, okay, and you consider this collection of groups, say so for almost everything I say, you can either put this 0 or not if you wish. If you consider all of these groups, I mean, a basic question is, are they actually different from each other? So we've given them certainly different names, but perhaps a priori it's not so clear that they're not actually isomorphic to each other as groups. And it turns out that this is, so to decide whether or not two such groups are isomorphic to each other is a surprisingly difficult problem. So you can sketch some of the history of that. So there's maybe one could start with something a priori simpler, for instance, the homeomorphism groups. So if you have two, so the homeomorphism group of a given manifold is just one group. Okay. If you want to compare two different manifolds, and so if they're compact at least, the homeomorphism groups are isomorphic to each other if and only if the underlying manifolds were homeomorphic as manifolds. And in fact, any isomorphism is induced by a homeomorphism between the two manifolds. That doesn't, so this wasn't known as a theorem until the late 1960s. And for diffeomorphism groups, there are some significant difficulties that arise, given by the fact that you can have, for instance, two manifolds that are homeomorphic to each other but are not diffeomorphic to each other, these so-called exotic smooth structures. And so, to answer the question of, are these groups distinct? It took some amount of time to give some sort of answer to that. So the first definitive result was a theorem which was not stated as such by Dawkins, but Dawkins did the bulk of the work, and one also can attribute this to Bachner, Montgomery, and also to the Kirch. And what they say here is the following. So let M and N be closed smooth manifolds. Okay. And suppose that K and L are natural numbers or infinite. So if you have an isomorphism of groups between diff K of M and diff L of N, okay. So then K has to be equal to L, and phi is induced by a CK diffeomorphism. That is to say, if you want to compute phi on a particular value of a particular diffeomorphism in here, you apply the inverse of a diffeomorphism between M and L, then apply that element and then push it forward. So it's just conjugation by a diffeomorphism. So, great. So what this in particular implies is that at least for integer values of R, all these groups are different from each other. None of them are isomorphic to each other. So if one tries to make the argument work for non-integral values of R, one encounters some serious issues. So they're technical, and they have to do with these sort of Hilbert's fifth problem sorts of issues of promoting a continuous action of some Lie group binding diffeomorphisms to a smooth action. And it's not clear how to make that work for non-integer regularities. Well, that's some motivation. Well, so a different motivation, which is
as soon as K is bigger than 1, these are all Lie groups, right?
well, infinite dimensional ones.
Sorry?
I mean, they're not finite dimensional ones. So a related problem which provides a secondary motivation for studying the difference between these kinds of groups comes from, well, originally from foliation theory, and it considers the following problem. So let G be a countable group of homeomorphisms of some manifold M. Let's just have it stay within the closed, smooth category here. Okay, so what is the highest degree of regularity by which G can act? So, i.e., what I mean is, so we want to compute the supremum of the R's such that G sits as a subgroup of diff R of M. Okay, so what this problem is really asking about is just how can we understand these very, very much uncountable, infinite dimensional groups in terms of their countable subgroups, or you can, if you wish, you can even replace this countable here with finitely generated. Okay, so now this problem is completely open in general. And as far as I know, there are only some examples for which this value is finite and known for one-dimensional manifolds. It's for some nilpotent groups and a few other examples. If you wanted to sort of turn around this question a little bit to understand the distinction between these groups, one can ask sort of a parallel problem, namely, is there a countable subgroup, or maybe even finitely generated, of diff R of M with no non-trivial action on M by CS diffeomorphisms, where here S, of course, should be greater than R. So this question, on the other hand, has an answer, at least for some manifolds. So there's a theorem due to Kim and someone else that says that, so the answer is yes for all R for M equal to the interval or the circle. So here, to be slightly more precise, I'll just say it in words to avoid writing too much, is in both cases of the interval and of the circle, one can find finitely generated groups where the finitely generated is uniform in R. I think it was like 5 generators for the interval and maybe 7 for the circle, which have the property that the commutator subgroup of this group of homeomorphisms is simple and infinite, not finitely generated. And so these are built for each regularity R, and any action by CS diffeomorphisms has a abelian image. So it's almost no non-trivial. So if you look at the commutator subgroups themselves, then they have no non-trivial actions in higher regularity. So that answers this question, at least when M has dimension 1. And it's completely open. Well, sorry. This critical regularity question: can you find countable subgroups of diff R with no non-trivial actions by CS diffeomorphisms? Is in general open for dimensions 2 and higher.
Sorry, so you only do this for countable or finitely generated? So
Okay, so if you want no non-trivial, then it's just countable. If you replace this with no non-abelian action, then it's finitely generated. There's a fundamental problem with trying to get no non-abelian because of this first instability theorem. Any finitely generated group of diffeomorphisms of the interval necessarily surjects to the integers, so you can't avoid that. Okay. So differentiability, just in general, I'd like to make a side remark, is it's very, very subtle as a property of groups, in the sense that you have some countable group, and you want to know if it acts by diffeomorphisms on some manifold, let's say even in some relatively simple case, like the interval or the circle. It's very difficult to decide if that's the case or not. So let me just make some side remarks here. So if G is countable, then G embeds in the group of orientation preserving homeomorphisms of the interval or of the circle, if and only if G is left, or I should just say linearly or circularly orderable. That's what so you can either put a linear order on G or a circular order on G, which is invariant under the left regular action of G on itself. So that's a classical result. A connection between this and logic is that actually linear and circular orderability are elementary classes. So linearly and circularly orderable groups form elementary classes. So this is a theorem. Let's make sure I get the names right. This is due to Girardet and Leloup. Right, so you can write down a countable list of first order sentences which are satisfied precisely by the linearly orderable groups or by the circularly orderable groups. That's sort of nice. But let's suppose that you ask the same question for diffeomorphisms. Right? So you want to know, does G embed in, say, diff 1, 0 of the interval, or diff 1, 0 of the circle? So then the answer is much nastier. So these such groups are not an elementary class. So what one can prove, in fact, is that there's a non-standard model of Thompson's group T, which acts by homeomorphisms on the circle. Well, it has to admit an action by homeomorphisms on the circle because it lies in this elementary class of circularly orderable groups, right? But one can prove that it doesn't actually act by diffeomorphisms. Right? So that means this class of groups is much more complicated. In fact, this is a theorem, maybe sort of, it's in progress, is that there does not exist an L omega 1 omega sentence defining such countable groups. And so if you look at in the Polish space of countable groups, and you try to write down which ones admit actions by diffeomorphisms on the interval or on the circle, this is not even a Borel subset. Right? So it's very, very badly behaved. So that's just an extended side remark. So why don't we return to the question that I posed at the very beginning of distinguishing between these diffeomorphism groups. So I wrote this question in the wrong place, so let's sort of leave it right here for now.
Complete analytic or just non-Borel?
It's complete analytic, actually. I think so. I mean, it's a sort of
Okay.
it's a sort of theorem. So take that with the appropriate health warning. Okay. So I'd like to state two theorems. So the first theorem. This will be manifold detection, manifold recognition. So let M be as before, and we'll let G be a group that sits between diff 0 infinity of M and G here and diff 1. So it's some group of diffeomorphisms which is at least as big as the kinetic component of the identity of the C infinity diffeomorphism groups. And so there exists a first order formula phi sub m, okay, which well, such that first of all G models phi sub m, and the second is that so if you take, if n is another manifold, so I'm, again, smooth and closed, although to be totally honest, you don't actually have to assume that it's closed or even compact, just that it's smooth. And you have some other subgroup that sits between diff 0 infinity of n and h and diff 1 of n, and if phi sub m is true in H, then M and N are diffeomorphic.
So the form is just in the language of groups.
Yes, it's just in the language. Sorry, I should have said that. Yeah, this first order form of phi sub n in the language of group theory. So there's just the binary operation and the constant identity, and that's it.
The diffeomorphism is C1.
Yes, so the thing is that so if M is a smooth manifold, then there's a unique C infinity structure on it that's compatible with that C1 structure. So it doesn't really matter.
Okay.
So it doesn't really make a difference if you say they're C1 diffeomorphic or C infinity diffeomorphic to each other. Great. So here's so this I mentioned one of the difficulties in sort of understanding diffeomorphism groups at the very beginning was the fact that diffeomorphisms or smooth structures are very subtle because you can have these exotic smooth structures, for instance, on a given manifold. So here's it's not really a corollary of this theorem, but it's a corollary of the proof. So I'll write it as a proposition. It says that there is so the same hypotheses. Okay, so there exists a sentence. I'll call it psi sub m in the theory of G, such that if H models psi sub m, then M and N are homeomorphic. And so what this gives you as a corollary is, for instance, there exists a sentence, maybe let's call it phi exotic, which is true in diffeo of some sphere, some topological smooth sphere. So what I mean by this is a topological n sphere which is perhaps not diffeomorphic to the standard n sphere. If and only if, let's call this sphere S, if and only if S is exotic. So you can distinguish between standard and non-standard smooth structures simply by one sentence in the language of group theory. So that's something that one can do with all that. I still am dodging this original question of whether or not these groups are all distinct. So maybe let's finally answer that. So the second main theorem is what we would call regularity detection. So, let M and G be as before. So as in the previous theorem that I had here. Okay. So let S be a rational number which is greater than or equal to 1. So the conclusion here is that there exists a formula rho sub S M of X such that the following conclusions hold. So, right, so if diff 0 S of M is in fact a subgroup of G, then there exists a G in big G such that G models rho S M G. Okay. So there is some formula which is true for some element inside of diff S of G, and conversely, if there exists some gamma that rho S M gamma is true. Maybe let me write that slightly differently. If G models there exists gamma rho S M gamma, then G is not contained as a subgroup of the union of these things. So in particular, if there is an element which satisfies this formula, then G cannot be realized as a subgroup of R diffeomorphisms for any R greater than S. So this is saying, in particular, there's a sentence that depends on this rational parameter S, and of course on M, which which distinguishes the theory of G with the theory of all smoother diffeomorphism groups. So then as a corollary, one obtains that for all R and S, you have diff R of M, say 0 here, why not, is elementarily equivalent to diff S of M if and only if they're isomorphic as groups if and only if R is equal to S. Right, so in particular, these groups are all distinct from each other. Okay, so in my remaining time, maybe I'll say a little bit about how one can actually do this distinguishing of different regularities and
So what's that supposed to say? It's on the top two lines identical.
This is elementarily equivalent.
Oh, sorry.
Yeah.
Yeah, sorry.
Right, so that's actually reminds me to remark something. That if one looks at, say, homeomorphism groups of
Sorry,
matter.
so aren't there at least one?
Yes, yes. So that's it's erased now, but that was a standing assumption. Right? So because if R, if you take the Holder exponent being like C0R, diffeomorphism, that's not a group anymore.
Oh, I see.
Yeah. So you need to have that assumption. All right, so just a quick remark about, say, QFA or something like that. So if you look at homeomorphism types of manifolds, so it's true that the two homeomorphism groups are isomorphic to each other of manifolds, if and only if they're elementarily equivalent to compact ones. And there's a single sentence which isolates each isomorphism class. And here we've proved something similar, that each isomorphism class so each diffeomorphism class of manifolds is isolated by a single sentence. But if you want to distinguish between all these diffeomorphism groups, there are, of course, uncountably many of them, and we only have countably many sentences, which is why this rational parameter comes in here. So you can build one sentence for every rational parameter, doing like a Dedekind cut. So there's no real reason that S has to be rational. So it suffices to take a real number which is parameter-free, definable in second order arithmetic. But you might as well take a rational. So. Okay. So, some ideas behind the proofs. So, if one wants to construct this sentence, rho S Sm, then one has to have some sort of good way of encoding different degrees of regularity within group theory. And so I mentioned at the very beginning this theorem with Kim that says that you have finitely generated groups that act with a specified degree of regularity on the circle and on the interval, and no smoother. So the idea behind constructing those groups is what actually feeds into the construction of these sentences themselves. So it starts with somehow a very, very basic observation. So if we, I'll just do everything here in dimension 1, and most of this generalizes in some way, at least, to higher dimension. So I'll say that a lot of these ideas are actually quite old now. There was a paper by Jenny Harrison in the 1970s where she constructed diffeomorphisms of manifolds in all dimension, which were not conjugate to diffeomorphisms that were smoother, just entirely based on the dynamics of how these diffeomorphisms act on points. Those formed obstructions to acting more smoothly. So, well, what can one do sort of very, very explicitly? Well, suppose that you have the interval like this. Okay, now, suppose that you have further some collection of, countable collection of intervals. So this will be, I'll draw them like this. Okay, so you have here J1, J2, J3, and so on. Okay, so these are sort of Ji, some collection of disjoint intervals. Of I, the interval, big interval. It could be S1 if you wish, it doesn't really matter. Okay, with the proviso here that at least in this linear ordering that the supremum of Ji should just be less than the infimum of Ji plus 1, so they don't share endpoints. Okay. So suppose that F is a homeomorphism, say preserving the orientation of I, such that the support of F is equal to the union of these intervals Ji. So it moves points exactly in these orange intervals and is the identity outside. And that for all, and also that there exists an alpha which is positive, such that if you look at such that for all I, there exists an xi in J sub I, so that f of xi minus xi divided by the length of Ji is at least alpha. So this may be a lot to parse. Let me just say it in English. So what this is saying is that there's a definite bound, so that when you apply f to this interval, there's some point in each of these intervals that gets moved at least alpha proportion of the way across this interval. And alpha is completely arbitrary, it just has to be positive. So it could be a half, it could be a tenth, it could be whatever you want. So under these hypotheses, so here's a fun proposition. If one wants to get a feeling for what these sorts of what these arguments feel like. So there is no way that f is smooth. So in particular, there is no diffeomorphism that satisfies these conditions. So it's clear that one can write down a homeomorphism that does this. I mean, you can write it down almost in coordinates, insofar as that's actually possible to write an infinite composition of homeomorphisms. But no such homeomorphism can be smooth. And what one can do is, so you can, want to get the statement exactly right. And so one can do this sort of game any regularity that you wish. Right? So let little r be a real number that's at least equal to 1. And so we'll write r equals k plus tau, where here tau is between 0 and 1, and k is a natural number. And we'll assume the following. So assume that f is a CR diffeomorphism of the interval. And similarly, we'll say that f is supported on this union of the intervals ji. So the same picture as we had here. We'll let n sub I be just some infinite sequence of natural numbers. And now we'll say that some index I lies in some a sub f. This will be the definition of the subset a sub f inside of the natural numbers. If there exists an x in j sub I, such that if you look at f to the ni of x minus x divided by divided by the length of ji here. Sorry, I forgot to say something. So we'll let here delta be some fixed parameter alpha, greater than 0. Right? We want this here to be greater than 0, and one should assume something about these. Oops, thank you. Right. Now one should assume something technical about these n sub i's that relates to r, namely that, that the supremum of n sub I divided by I to the k minus 1 plus tau is less than infinity. So these are this is some sequence. Okay, I said it was infinite. Okay, it can't grow faster than this exponential. Than this polynomial function in I. Okay. So you look at the indices for which this is true, right? So you are looking at exactly the same thing as you were here in the continuous case, except now you're replacing the power of f that you apply by this n sub I. So you're allowing yourself to take larger and larger powers of f as the index grows to infinity. Okay. So then the proposition here is that the limit as n goes to infinity of, you take a sub f and you intersect it with the interval 0 to n, and you divide this by n. You take this size here. This is equal to 0. So this is, again, to unpack this in normal English. What this is saying is that if you have a CR diffeomorphism that is supported on a disjoint union of intervals like this, okay, then you look at how quickly can points move across each of these intervals. Okay, well, if you take the nth power on the ith interval, okay, then almost certainly that there will be no point that moves at least alpha of the fraction across. So this is the generalization of this proposition that I wrote up there for arbitrary CR diffeomorphisms. How much time do I have left? So you're supposed to be 55 minutes or okay, so I can tell you a quick converse to this characterization. Right, so here I said that, okay, if we look at maps that have this property where you're moving a definite proportion of the way across each of these intervals of support, then certainly you can be a homeomorphism, but you cannot be a diffeomorphism. And so now I've given you an obstruction to being a CR diffeomorphism, and as a positive result. Now, if we say instead, so same setup as before, and so if I take the infimum over all I, and I take the length ni times the length of ji to the k minus 1 plus tau, and this is greater than or equal to 1, then there exists a CR diffeomorphism F, whose support is equal to exactly to the union of these JIs, and for all I, there exists an XI in JI, such that if I look at F to the NI X minus X over JI, this is greater than alpha. So you can, under these growth conditions, if these intervals are not shrinking too quickly, then you can build a diffeomorphism that's of that regularity and moves points definite distances. So maybe I'll just say, so what does this have to do with first order logic? And well, so the power of the expressive power of the first order theory of a diffeomorphism group or a homeomorphism group is such that it allows you to say a very large, substantial amount about the topology of the underlying manifold. In particular, you can talk about things like points and open balls and the like. And so it becomes possible to literally encode the construction of an element of the ambient group which has these dynamical properties. And so then you can literally build a sentence that is satisfied by some group element if it has these sorts of dynamical properties. And you can, and that's again where the rationality of this exponent comes into play, that because you have to be able to talk about this sequence of natural numbers as an object in the language that you are studying. And that's possible, for example, if you encode the sequence as a constructible real number. So maybe I'll stop here.